So we're going to continue our lesson on properties of waves and vibrations. So let's look at our objectives for part 2 here. The first is identify how waves transfer energy without transferring matter. So how does that energy actually move through the wave? The second is to look at 3 different types of waves: transverse waves, longitudinal, and surface waves. And then the third concept is describe what happens when 2 waves interfere with each other. All right, so let's define a wave in terms of how the energy, or sometimes we use the word disturbance, travels through a medium, okay? And it travels from one location to the other. Now, the medium is whatever the wave is traveling through, right? So that could be air or water or solid materials, or in the example of the people doing the wave below, right, the medium are human beings, okay? But the medium just refers to the material that the disturbance or energy travels through. Now, if you notice, when you do the wave, right, people are moving vertically up and down at the right time so that the wave passes through them and then continues on to the next person. So we would say the energy here is moving from left to right, or the disturbance is moving from left to right. But notice the medium, the people themselves, stay in one location. They don't move with the wave. And this is true for really how all disturbances or energy moves through a wave. The medium itself may temporarily change its location, but it does not travel along with the wave through the medium. Let's look at another example here, Slinky, right? The toy with all the coils here that you probably played with before. If we were in the lab together, we would break out the Slinkies and have some fun. So when you stretch out a Slinky, right, the individual coils reach an equilibrium position or a rest position, and they're going to space themselves pretty evenly from one coil to the next throughout the length of this Slinky. Now, if we take the first coil and repeatedly vibrate it back and forth, in other words, kind of push and pull with our hand, it creates a disturbance that travels through the Slinky from one end to the other. You can see as you push, right, the coils become more compressed, they get closer together. And then when you pull back, right, the coils are going to expand and actually be further apart than their resting position or equilibrium position. So this creates a series of disturbances where the coils are close together and then far apart, and that will travel down the Slinky. Now, obviously, the metal in the Slinky is not traveling with the wave, right? But it is going to move temporarily around its equilibrium position. So here's kind of a little animation down below. You can kind of see how the wave moves through. So here's the big idea, right? The particles of the medium are only temporarily displaced from their resting position. Remember, for simple harmonic motion, the object is going to have a restoring force around its equilibrium or resting position. That's exactly what happens in a Slinky or spring. So there's always that force that's acting to restore them to their original position, and the wave transports the energy, not the matter. The material itself does not move with the wave. All right, let's look at different types of waves here. The first is a transverse wave, and this is where particles of the medium move in a direction that is perpendicular to the wave. Okay, perpendicular is the key word here. So if you look at the string or the rope in the example here, right, we flip it up and bring it back down. So notice the wave in the string is displacing the string vertically. It moves it up and then back down again, right, as the wave passes through it. So you've done this before, right, taking a rope or a jump rope and flip it. So some examples of this turns out to be certain types of seismic waves when we have an earthquake, how that energy travels through the Earth's crust. But maybe the more common examples are a vibrating string on a guitar, right? When you pluck a guitar, you're creating a transverse wave on that guitar string. Same thing with the piano, right? A traditional acoustic piano will have strings that are hit by a hammer when you press the key, and it creates a transverse wave traveling along those piano strings or wires. Another example is electromagnetic waves, right? We'll study those more when we get into light. So the key is vertical motion of the medium. Here's just another illustration that shows a whole series of particles. And you can see it looks like the wave's kind of moving left to right here, but if you focus on any one of those particles, you'll see that their motion is only in the vertical direction. They are not moving left to right horizontally. So another example of a transverse wave. The other kind of wave is a longitudinal wave. So this is where particles of the medium move in a direction that's parallel to the direction that the wave moves. So probably the most common example of this, there aren't as many as the transverse wave, is a sound wave. So think of a sound, right, as a disturbance that travels through the air. The air molecules themselves are pushed closer together and then farther apart. And if we do that at a certain frequency, our human ear, right, can detect those slight changes in pressure in the form of a sound wave. So this is the basis for how a speaker works, right? If you have a speaker, whether it's an earphone speaker or a speaker in a, for a large room, it's the same concept. It has a speaker cone or diaphragm represented here by the red line that vibrates back and forth. So as it goes forward, right, it compresses the air molecules, and then as it pulls back, it creates a area where the molecules are further apart. So again, pick any dot here. It really looks like the dots are traveling left to right, but it's the energy that's traveling, not the medium itself. If you look at any one of those dots, you'll see that they are just vibrating or oscillating back and forth around some equilibrium position. Okay, so that is the concept of longitudinal. It moves parallel to the direction that the wave moves. So let's just do a little check here. Look at these two waves, watch their little animation, and see if you can determine which one is longitudinal, which one is transverse. So we're getting kind of a three-dimensional view here a little bit of a wave traveling through a surface or a sheet of material. All right. So the first one, right, the medium is moving up and down compared to the direction of the wave moving left to right. And in part B, it's moving parallel to the propagation or direction that the wave is moving. So part B would be longitudinal because it's moving parallel to the wave. Part A would be transverse because it's moving perpendicular to the wave. Now, there's one more type of wave. We're not going to do a lot of work with this, but it's maybe what you first think of when you think of waves, right? Is waves on a lake or waves in the ocean. If you go out to the beach here, right, and watch the waves roll into the beach. So these are neither transverse or longitudinal. They're kind of a combination. But what happens in a wave is that the particles of the medium undergo a circular motion. Right? So if we could look at the individual water particles kind of slice down through a wave, that's what this animation is showing us here. You would see, particularly right at the surface, those particles, they move up and forward and then down and backwards and trace out a circular path. Now, as you get further underneath the water, right, the wave action is not as significant, right, to where their movement is much less, but it is still a circular motion. So this is the phenomena that we use to describe water waves or energy traveling through a water wave. All right, last very important concept here, and that is interference of waves. So what happens if two waves traveling on the same medium, material, or object interact with each other? Okay, we call that interference. And what happens is we get a displacement, right? Displacement means how far is the material moving from its equilibrium position, caused by two or more waves. And it's simply the algebraic sum of the displacement of the individual waves. So just watch this animation for a second here, right? We see two waves, a black one coming from the left and another black one coming from the right. The one from the left is larger, the one from the right is smaller. So when two waves cross each other like this, they basically pass through each other. But when they're overlapping, their amplitudes are going to add together. So notice we get a resulting wave in the center right when they interact with each other that is larger than either of the individual waves. And that's what we call interference. Okay. So let's look at this a little bit more detail here. There are two types of interference. And let me back up here. Another word you'll see and used in the lesson and in the assignment is superposition. It just means one wave on top of another or interfering with each other. Okay. So we have a case of constructive interference. That's when two crests or peaks of the wave align. They would add together and create a increased amplitude. Okay, so watch how the green and the blue wave interact here. Right there is constructive interference. Notice the black is the sum of the two waves together. And then they reach a point where they have destructive interference. This is where one crest lines up with the other trough. So you can think of a negative amplitude and a positive amplitude. If they're equal to each other, they're going to cancel out, right? +5 and a -5 gives us 0. Same concept here. We're adding the sum of the two wave amplitudes. And we do it algebraically, which just means we pay attention to whether they are positive or negative. Okay, so the assignment today you're going to work on is going to have some questions about how waves move through medium, the different types of waves, and then some activities for you to do where you're actually going to work with two waves and add their amplitudes together and see what the resulting interference or superposition wave would look like. All right, so we understand how energy transfers through a wave. We understand that there are three types: transverse, longitudinal, and surface, and how to tell them apart and recognize them. And the third is what happens when two waves interfere with each other. We get either constructive, where they add together, or destructive, where they cancel each other out. All right, that's it. Take a look at the lesson.